Ladies and gentlemen, please observe the graph. So the graph show that Q against T. That means that this graph show the charge. Okay, the charge stored in the capacitor during the process of charging. Q naught will be the full charge of the capacitor. So this means that Q is at any instant. If the Q at any instant, that means Q naught times, we use the formula Q naught times with 1 minus E negative T over RC, as shown in the diagram. So what happened? We look at here. From the formula, where Q equal to CE times 1 minus bracket 1 minus E negative T over RC, where I is equal to dQ over dt, and I naught is equal to EMF over R. Differentiate. Let's differentiate the equation. We get that dQ over dt, dQ over dt, that means that the charge over time will be the current. And finally, we get that current I is equal to I naught exponent negative T over RC. Where from the graph just now, we get that the formula for the current in capacitor. Okay, the current in capacitor, current during the processing of charging of a capacitor, I equal to I naught epsilon exponent negative T over RC. Let's go through the next slide. The graph show that current in the circuit across the time of charging. So just now we get an I equal to I naught exponent negative T over RC, and then we notice that the current reduced with time. So what happened is we notice that I equal to 1 over E I naught is equal to 0.36 at I naught, which means it is 37% of its initial value. And the second, I is equal to 1 over exponent square, where it will be equal to 0.135 I naught, which is 13.5% of its initial value. That means that the current reduced during the charging process. When the charging time increase, the current in the circuit will reduce. This means that we get that the charging time, okay, so this means that for I naught equal to the time of RC, if R times C will be the time where the current reduced from initial, okay, that means that, okay, the time is 37% of its initial value. The current reduced until 37% left. Once true RC, the time equal to true RC, the charging time equal to true RC, that means that how much of the current remain? It just 13.5% from the initial current remain, where the initial current is E over R. That means that voltage of the battery, voltage of the charging source divided by the resistance of the resistor. Okay. Next. Derivation of V as a function of T. T. As we know that E equal to VR plus VC. VR is the potential difference across the resistor, and C is the potential difference across the capacitor, where EMF is equal to IR plus with V, where V is the potential difference across the capacitor. Next, from E equal to VR plus V, which is equal to IR plus V. This V is the potential difference across the capacitor, voltage of a capacitor. And the charge of the capacitor Q equal to CV. The charge means that during fully charged. Okay, when fully charged, Q equal to CV. And the current is equal to dQ over dt. That means that dCV over dt, that means that it will be equal to C dV over dt. Substitute the equation. So we get that. Finally, we get that V is equal to EMF times with 1 minus exponent negative T over RC. That means that the expression for the voltage or for the potential difference across the capacitor is equal to EMF of the battery of the charging source times with 1 times with bracket times with 1 minus exponent negative T over RC. Let's look at the graph. The graph shows that the voltage across the charge capacitor. The voltage across the capacitor during the process of charging. V equal to V, the voltage of the capacitor is equal to EMF times with 1 minus exponent negative T over RC. From here, okay, the charging time, what will happen is, if V equal to 0, what happened? V equal to E, and V equal to E times 1 minus exponent negative 1. Okay, so from here, if the V is equal to 1 minus 1 over E times E, where this E, this equation, equal to this part. Okay. So when V equal to 0, V is equal to 0. That means that the T also equal to 0. When V equal to E, what will happen if is the V equal to E? V equal to E means, well, the V voltage of the capacitor equal to the charging source. That means that the second step is fully charged. The first step is the capacitor in not charged condition. None of any charge in the capacitor. Number 3 means, well, the voltage or the potential difference of the charging capacitor at this moment. What is the moment? That is the T. Okay, the charging time constant T. So that means this will be the voltage. Now observe the graph. Okay, so what will happen during charging? What will happen? Voltage will increase. The charge also increase with time. Just the current reduce with the time. As a conclusion, we can say that in charging process, we notice that Q is equal to Q naught bracket times bracket 1 minus exponent negative T over RC. Okay. Next, for current reduced with time, where the equation I equal to I naught exponent negative T over RC. And last, V will be V against time, V increase with time, where V, the voltage of the capacitor, equal to the EMF times bracket 1 minus exponent negative T over RC. As a conclusion, okay, these are the three equations for the charge, for the current, for the potential difference in a capacitor during the charging process. And the graph for the charge and the potential difference both of them are increased with time, where the current reduced with time. These are the process of charging of a capacitor. What will happen? How is the formula? How is the condition when a capacitor is discharged? Discharge means that we release the charge from the capacitor. Let's say now we look at the potential difference across the capacitor. The potential difference across the capacitor now, the potential is maximum. The voltage is maximum, where now the circuit is lost connection, not connected. So that means that the current is minimum or zero. Please observe what happened to the voltage, what happened to the current, and what happened to the charge. Okay, now the capacitor is fully charged, so that means it's from the highest point, maximum point. Okay, voltage also from maximum point. Okay, current from minimum point. So what happened is like this. Okay, so we observe again. Observe again what happened. Voltage and charge, no problem. Let's look at the current. Look at the ammeter. What happened to the ammeter? Ready? Go. Notice or not? When fully charged just now, the current becomes zero. Once during discharge, when the circuit is connected, the current become maximum. That means that during the discharge process, the charge in the capacitor Q, the potential difference across the capacitor, and the current, all of them are reduced exponentially from the maximum. Okay, let's go to the next slide. Now, as we know that VR is equal to IR, VC is equal to Q over C. And where this is Q from the Q equals CV, yeah? I equal to dQ over dt, where because the Q decrease with time. So negative, why negative? Because it is in the process the charge reduced. And equality, VR equal to VC. VR is equal to VC. So IR equal to Q over C, and substitution, we get that negative R dq over dt equal to q over c. And integration, the equation, integration both sides, and we get that the q is equal to q naught e negative t over rc. Just now it's 1 minus something, right? Now normal 1 minus. Okay, this is the formula for the charge for the q during discharging of a capacitor. The graph of charge against time show that the q, the charge reduce with time. Okay, where the time equal to RC, the time equal to RC, that means that 1 over E times with, it will be the Q is equal to 1 over E Q naught. Okay, 1 over E Q naught, where the time equal to RC. Okay, so that means that this will be, you see, T. When the T, this T equal to RC, that means that negative RC over RC, that means that RC over RC is 1, right? That means negative 1, i.e. the power negative 1. That means it's 1 over E. You see? Okay. Next. Okay. This one. Okay, for the graph. Okay, from here we get that Q equal to Q naught E negative T over RC. The current is equal to dq dt again. So substitution I is equal to negative D. Okay, Q, the change, the discharging of charge. That's in Q naught exponent negative T over RC over dt, and differentiate, and last substitution to the equation, we get that current I equal to I naught exponent negative T over RC. Okay, so from here we get that the graph is reduced exponentially with the time. Now, if the current I equal to I naught exponent negative T over RC, what happened? Okay, for the equation, so the Q equal to C, Q not equal to C, V not Q, where Q equal to CV, and the discharging current I equal to dQ over dt. Negative, yeah. Negative means that decrease of the current. Negative means that the process of discharge. Substitution the equation, we get that the potential difference IR equal to negative RC dV over dt, and integrate the equation. At the end, we get that V equal to V naught E V naught exponent negative T over RC. Okay, so we get that V reduced exponentially with the time. And V is equal to, notice that once V reduced exponentially with time, that means that at the T, the time taken is equal to RC, that's in negative RC over RC, 1 over E V naught. Okay. As a conclusion, summary, we notice that the graph of Q over T, the Q reduced with time, where Q equal to Q naught exponent negative T over RC. For the current I equal to I naught exponent negative T over RC, where the current also reduced exponentially with the time taken. Next, V equal to V naught exponent negative T over RC, where V naught reduce with the time again. So as a summary, the process of discharging of a capacitor, the Q, I, and V have the same same polar or same pattern, where all of them reduce with the time. Okay, and where the formula, we notice that when the discharging time of RC, okay, discharging time equal to RC, that means that the Q will be equal to 1 over E Q naught, or the current also will be 1 over E I naught, and V equal to 1 over E B naught. Ladies and gentlemen, let's look at another slide. During the process of lightning, okay, the lightning produced with very high voltage. So what happened during lightning? Initially, the building with charge negative or charge positive, you see, if the building charge positive and negative, you notice or not, depends on what are the charge on the cloud. If the charge on the cloud is positive, it will strike to the building which charge opposite charge. Okay, so you see negative to positive, positive to negative. Because the charge on the building, consider is the stationary charge on the building. So the charge on the cloud means that it's more easy to move through. So at the end, the lightning produced. Let's refresh back what we learned in previous chapter. What is meant by potential difference? Potential difference means that it is the energy used to move a charge from one point to another point, right? In an electric field. Consider the distance of the positive charge and the negative charge. The charge on the building and the charge on the cloud. Both of them with a very far distance. Okay, very far distance. If the charge able to move from the cloud to the building with a very big distance, means the potential difference across both, okay, building and the cloud also terrible big or large. Means if somebody struck by the lightning, actually consider, or in other words, we can say that the people, that person struck or shocked by a very high voltage of current. Why? Because big potential difference, large potential difference. Okay, so okay, they are two types of lightning discharge. What are that? Cloud to cloud lightning occur between the opposite charge in a cloud. Okay, so that means that cloud to cloud lightning. In the cloud also have the positive charge and negative charge. So that means that sometimes we notice that on the sky, when lightning produced, the lightning is moved vertically. Oh, sorry, move horizontally. Horizontally, that means from the cloud to another cloud. That is because both cloud with opposite charge. Another one is the cloud to ground lightning. That means that just now like the building and the cloud with opposite charge. So at the end, they produce the lightning from the cloud to the ground. So, ladies and gentlemen, come to the end of our lesson today. So, before I end this lesson, later, ladies and gentlemen, later I will post the exercise on our Telegram group together with the answer. So what I want you all to do, please solve the question after lesson. And you check the answer after you finish you try and finish the question. Don't just copy the answer straight away. So from here, these are the questions for the charging and discharging of capacitor. Question 1, question 2, question 3, question 4, question 5, question 6, question 7, and finally, question 8. So thank you and very much for my student to attend my class today.